Hello everybody, welcome back to the next lecture, which is on laser spectroscopy. So the last lecture, as those of you who already watched that might have seen, was fairly long, and so the lecture in optical spectroscopy is normally a little bit more than 2 normal lectures occasions, while the laser spectroscopy is a little less than 1. So this lecture will be considerably shorter than the other one. And the main reason for that is that we have already discussed many of the things which will come up in the laser spectroscopy lecture quite extensively. Most notably the detectors, which are often exactly the same detectors as you use for optical spectroscopy, and where the most common one is probably the photodiode, which we discussed extensively. And many of the properties which we discussed in the optical spectroscopy lecture for the detector, like the need for low noise and the need for it to be fast, is even more true in, I would say, or it is at least equally as true for laser spectroscopy applications. So let's start to compare. The setup which we used for optical spectroscopy to the setup which we use for laser spectroscopy. And we will start off with a light source, which is obviously different, and then we will also discuss the sample, which turns out that due to the properties of a laser, which is predominantly that it has a very well decided frequency, so very organized light source with well-defined frequency or wavelength, and also very spatially organized. It has a very nice optical mode, which means that you can do some very nice things with a sample as well. Okay, so let's get started. So the first thing is, of course, that we replace the broadband light source which we had when we did optical spectroscopy for a narrowband tunable laser. Not always, as we will see later, but for the first applications we will use a narrowband source. And since our source now only has a single wavelength, that means that we already know what wavelength our source have. So that means that we don't need a spectrally resolving instrument anymore. So because we know what wavelength our laser have, and therefore we only also need a single point detector which measures how much of a wavelength the laser has was absorbed. And the spectral width of a laser can be much more narrow than the spectral resolving instrument, when the bandwidth of a spectral resolving instrument, where there are lasers below 1 Hertz, which is very narrow, considering that the frequency of light is 500, about in the visible range is about 500 terahertz. Okay, so far our laser only has a single frequency or a single wavelength. So how do we go about getting the spectra from our sample? Well, what we can do is that we can keep the intensity of a laser stable, or what we would like to do is keep the intensity of a laser stable, but we would like to sweep the frequency of a laser with time. So that means that we need to do this kind of laser spectroscopy, we need a laser which can sweep, which can change it. There is some sort of input so that you can change the frequency of the laser as a function of time. If we then have our sample with an absorption, for example, like this, so in this case we have absorption, that means that when we get to this wavelength or this frequency, then there will be some of the light absorbed. So if we look at the light coming out here afterwards, it will look something like this. Corresponding to this frequency here, there will be a small dip in the light. And we record this as a function of time. But as we know how we change the frequency of laser as a function of time, that means we have a conversion factor from time to frequency, so we can change our scale here to frequency afterwards. And we have our spectrum with potentially very high resolution. So this is the principle behind the most common laser spectroscopy and the first laser spectroscopy setup which we will be discussing. Let's start by discussing a few different laser sources. So the laser which we then send through the sample. And as an example, not of a laser which can be tuned and used for spectroscopy, but because there's quite a lot of interesting parts which are sometimes used for spectroscopy in this laser, let's discuss a green laser pointer. So these can be bought for as little as about 100 crowns. And if we look inside them, the green laser pointers are a little bit special. So you start off with an infrared light emitting diode, and we'll come back to light emitting diodes in a little bit. And then after that you have a lens which focus the light which comes out from this into a neodymium doped laser crystal. That's this first part here. And inside there, the 808 nanometer light inverts the neodymium ions. And then they laces, so there's a mirror here and there's a mirror here, and they laces on 1064 nanometers. So 1064 is also in the infrared, and we wanted green light. So the next thing you have to do is frequency double the light. So that means that you go from 1064 nanometers to 532 nanometers. And I will talk about a little bit about how that's done, because that's important for spectroscopy. For example, for Project D, they are doing, in that case, different frequency generation, but this nonlinear frequency generation is a very important part of lasers and laser spectroscopy. And then, so then you have a beam coming out of green light now, and then you have two lenses which collimates the laser, and then you have an IR filter which, at least on slightly better modules, which blocks the 1064 nanometer light. And all of this can be sold for so little money, and it has to be fairly well aligned to work. So that's and give a good beam quality. So that's actually quite remarkable. Okay, so I said I would say a little bit more about, you have already talked about inverted crystals and lasing before, but I thought I would talk a little bit more about the double frequency generation.